David Williams here, and talking to you about JFET small signal models. And what we're going to do in today's video is figure out how to go from a circuit like this one right here, to a circuit like this one right here. And we'll actually even take that a step further, and from a circuit like there, well, I guess in a later video we'll take it a step further. Going from a circuit like that, how do you figure out what the input impedance, what the voltage gain, and what the output impedance is? So I guess to make this a little bit more precise of this circuit to this circuit, we should actually have some kind of input signal coming from what's called VA, some sort of source voltage, and then also going to some kind of load that the output signal is going to be applied to. Oh yeah, and one other thing I guess that should be here is the coupling capacitors right there. This is my R load. And here's the same circuit and a graph that hopefully you are now familiar with, that's relating the gate source voltage to the drain current for this particular transistor right here. And so in this case we've got a pinch off voltage, or a gate source off voltage of -6 volts, and an IDSS, or drain source saturation current, of 12 milliamps. So that's that point up there. And this is the DC model. So what we do, or we've looked at this when looking at the DC model. And so what we're going to do is, for a particular circuit like this one here, there will be a DC operating point. So let's say the operating point for that particular circuit was right here at about -3 volts and 3 milliamps for the ID. And then what's going to happen is, when we apply an AC signal here, so we've got an AC signal connected from some kind of source, a source voltage, that AC signal is going to be applied on top of the DC, and what you're going to get is your gate source voltage will swing back and forth on this line, and your drain current is going to change accordingly, which is going to affect what your output voltage is going to be. And if we were to look at a small enough signal being applied on top of this DC, we can do, this is why we call it a small signal analysis, because it's small compared to the DC operating points. We can approximate the swing as being just a straight line that's sort of, that is tangential to this point here. And we get the swinging we can approximate as being along this line as opposed to along the black line. So we can have a delta VGS, a change of VGS there, and a delta ID here. And the slope of that line is the rise over the run, and the slope of that line is going to be approximately how the gate source voltage changes when the ID changes, or I guess I should say how the ID changes when the gate source voltage changes. And that slope of the line, the delta ID over the delta VGS, we give that a name. We call that, well, we give it the symbol GM, and that G with the subscript M is called the transconductance. And this term transconductance comes from what is that called, a portmanteau, a putting together of two words. So the conductance is coming from the fact that we have a relationship between voltage and current, and it's an inverse relationship. And the trans comes from the fact that we were talking about a relationship between a couple of things. And it's not a constant. This GM is not a constant. The slope of the line there is different than the slope of the line here, and different than the slope of the line down here. And in fact, I've done an example here. I've got a different transistor. You can see that the IDSS is 10 milliamps and the VGS off is -5 volts. And I've done some calculations on what the GM is at some different points. So down here we've got a GM at this point right here. We've got a delta VGS of about 1.1 volts for a delta ID of 1.5 milliamps, and that ratio gives me 1.36 millisiemens, the unit for conductance. When you have current over voltage, it's the conductance is the unit. So we've got 1.36 millisiemens there. We go up the graph a little bit, and we draw a tangent to that point on the graph, and we approximate what the delta ID is and what the delta VGS is, and we get 2.75 milliamps over 1 volt for a transconductance of 2.75 millisiemens. And then further up, we've got an even steeper slope. So our delta ID for our given delta VGS is going to be bigger. So we've got 3.5 milliamp change for ID for a 0.875 volt change in the VGS to give us a VGS of 4 times 10 to the minus 3 millisiemens. So the further up we go in the graph, the more our transconductance is going to be. And of course, right here, this is the highest it's going to be. This is the highest ID value we're going to have. And it's the steepest point on the graph, and so that's where the GM is going to be at its highest. Now here's a calculus alert. Because when we're dealing with slopes of lines that are tangent to another graph, like this curve here, this transfer curve for the characteristic, and we're drawing lines that are tangent to points, what we're talking about is the derivative of that graph at that particular point. And that is, in fact, what the GM is actually the derivative of ID with respect to VGS. And guess what? We know what the equation for ID is. Remember from Shockley's equation? ID is equal to IDSS times 1 minus VGS over VP, and then that's all squared. So we could take that equation and plug it in here into the GM equation, and then take the derivative of the equation with respect to VGS, and we could figure out what GM is actually equal to. And if you go through the steps, I'm not going to do it for you actually. I'm going to leave it to you as an exercise if you want to go through all the steps to figure it out. What you get is GM is equal to 2 times IDSS over the magnitude of VP times 1 minus VGS over VP. That is the equation for GM. And you can see that GM is going to be at a maximum when VGS is 0. And so that's going to be when ID is equal to IDSS, so it's this point here, and that's sort of what we intuitively figured out. This graph is getting steeper and steeper and steeper. That's the maximum point that we can have for ID. So that must be the highest value that we can get for GM. And we can define that point, or I should rephrase that, we do define that point, and we call that the GM naught, or GM 0. And that's equal to 2 IDSS over the magnitude of VP. So what we can say then is that GM, just to shorten things down, is equal to GM naught times 1 minus VGS over VP. So for example, if we have a JFET that the characteristics of this particular JFET are that the IDSS is equal to 10 milliamps and the VP is equal to minus 5 volts. We want to find GM at some different biasing points. So if we find GM at VGS equals 0 volts, well, then we take this 0 volts, plug it into this equation here, or ultimately really it's this equation here. We get GM is equal to 2 times IDSS, that's 2 times 10 milliamps, over the magnitude of VP, which is 5 volts. And that works out to 4 millisiemens. And of course, and when VGS is 0 volts, this is the maximum that GM is going to be. So this is also equal to, in this case, this is equal to the GM naught. So we can use this number now when we want to calculate, for example, VGS is equal to minus 1.6 volts. We can calculate GM to be equal to GM naught times 1 minus VGS over VP, which is minus 5 volts. And this works out to 2.72 millisiemens. So the GM, of course, is dropping as we decrease VGS from 0. And if we decrease VGS equals even more, for example, at minus 3.2 volts, plug that number into the GM equation, and you get a GM of 1.44 millisiemens. And in fact, the examples that I had back here, this is the same JFET. So at the same 3 different points, I've calculated a GM of 1.36 millisiemens, just from I graphically figured out 1.36 millisiemens, where the actual numerical method figured out using the equation I got 1.44 millisiemens, so pretty close. 2.75 millisiemens for the second point here, and calculating it I figured at 2.72 millisiemens, so again pretty close. And up here 4 millisiemens from the graph, and I got 4 millisiemens from the equation. Now why is that GM value so important? Well, when we are trying to come up with a small signal model, we need to know that transconductance value. Here we have a gate, drain, and source of a JFET. That's how it would look like in a schematic, but if we want to draw this in the small signal model, we're going to replace that schematic with the AC equivalent model. And what we have here, the gate, and down here the source, and we've got some voltage between the gate and the source, so we'll call that VGS. And then what we have in between the gate, or sorry, not the gate, the source and the drain, we have a current source. And that current source is dependent on, well, that current source is actually uses the GM value, and it uses the gate source voltage. Capital G there. It uses the gate source voltage. So the current in this current source is equal to GM times VGS. And what else do we have? We've got, so it's connected to the drain, and then between the drain and the source we have another resistance that often called RD, and this is hopefully really big, and so we can consider that an open circuit, but it may not be big and we may have to take it into account. Okay, I want to do one example of converting a JFET amplifier circuit into the small signal equivalent. Let's say we've got some kind of input signal connected into a JFET circuit. Got the RD value here. We're connected up to VDD. The output's going to be taken here. This is going to be therefore a common source amplifier. And then we've got the RS connected here, and then bypassing the RS, as far as AC is concerned, is a capacitor. One more thing, we've got another biasing resistor there, RG. So we want to convert this into the AC model. So what we need to do, well, similar to what we did with the BJT circuits, we short all the voltage sources. So VDD here will be now connected, it's shorted, so it's going to be connected straight to ground. This capacitor, and this capacitor will all be shorted. And what I get is VN connected here, connected through RG, and across RG will be my VGS, and then over here is my source. So there's my gate. I guess I could draw it. There's my gate there, and here's my source on this side. Source is connected to ground. This source was shorted through a capacitor, so the source is going to be connected straight to ground. Between the source and the drain, I've got this current source, VGS, GM times VGS, and then between the source and the drain I also have this little RD value, and then that's going to my V out. Oh yeah, one more thing, I've got the RD, also this big RD connected at the drain here, that's going to be connected straight to ground also. So big RD. So converting from the schematic to the AC small signal model, I've done it. I've just done it right here. Again, RD is just a characteristic of the JFET, and hopefully our little RD is really big, and we can say if that little RD is a lot bigger than the big RD, then we're going to ignore little RD. Okay, the next videos are going to be showing how to convert this particular circuit into an amplifier circuit. So that small signal model, convert it into this model where I have my Z in, I've got my voltage gain, AV times V in, and I've got my Z out. So basically I'm just trying to figure out these three parameters. What's the input impedance of that amplifier? What's the output impedance of that amplifier? And then what's going to be the voltage gain of that amplifier. So hopefully you learned a little bit about small signal models of JFET amplifiers, and I'll see you in that next video.